Twincharger refers to a compound-forced induction system used on some piston-type internal combustion engines. It is a combination of an exhaust-driven turbocharger and an engine-driven supercharger, each mitigating the weaknesses of the other. A belt-driven or shaft-driven supercharger offers exceptional response and lower PM performance as it has no lag time between the application of throttle and pressurization of the manifold. When combined with a large turbocharger if the turbo was used by itself, it would offer unacceptable lag and poor response in the lower PM range. The proper combination of the two can offer a zero-lag power band with high torque at lower engine speeds and increased power at the higher end. Twincharging is therefore desirable for small-displacement motors, especially those with a large operating RPM, since they can take advantage of an artificially broad torque band over a large speed range. Twincharging does not refer to a twin-turbo arrangement, but rather when two different kinds of compressors are used. Technical description: a twincharging system combines a supercharger and turbocharger in a complementary arrangement, with the intent of one component's advantage compensating for the other component's disadvantage. There are two common types of twincharger systems, series and parallel. Series the series arrangement, the more common arrangement of twinchargers, is set up such that one compressor's output feeds the inlet of another. A sequentially organized supercharger is connected to a medium to large-sized turbocharger. The supercharger provides near-instant manifold pressure. Once the turbocharger has reached operating speed, the supercharger can either continue compounding the pressurized air to the turbocharger inlet, or it can be bypassed and/or mechanically decoupled from the drivetrain via an electromagnetic clutch and bypass valve. Other series configurations exist where no bypass system is employed and both compressors are in continuous duty. As a result, compounded boost is always produced as the pressure ratios of the two compressors are multiplied, not added. In other words, if a turbocharger which produced 10 psi alone blew into a supercharger which also produced 10 psi alone, the resultant manifold pressure would be 27 psi rather than 20 psi. This form of series twincharging allows for the production of boost pressures that would otherwise be unachievable with other compressor arrangements and would be inefficient. However, the efficiencies of the turbo and supercharger are also multiplied, and since the efficiency of the supercharger is often much lower than that of large turbochargers, this can lead to extremely high manifold temperatures unless very powerful charge cooling is employed. For example, if a turbocharger with an efficiency of 70% blew into a Roots blower with an efficiency of 60%, the overall compression efficiency would be only 42%, at 2.8 pressure ratio as shown above and 20 degrees Celsius ambient temperature, which means that air exiting the turbocharger would be 263 degrees Celsius, which is enough to melt most rubber couplers and nearly enough to melt expensive silicone couplers. A large turbocharger producing 27 psi by itself, with an adiabatic efficiency of around 70%, would produce air at just 166 degrees Celsius. Additionally, the energy cost to drive a supercharger is higher than that of a turbocharger. If it is bypassed, the load of performing compression is removed, leaving only slight parasitic losses from spinning the working parts of the supercharger. The supercharger can further be disconnected electrically, which eliminates this small parasitic loss. With series twincharging, the turbocharger can be of a less expensive and more durable journal-bearing variety, and the sacrifice in boost response is more than made up for by the instant-on nature of displacement superchargers. While the weight and cost of the supercharger assembly are always a factor, the inefficiency and power consumption of the supercharger are almost totally eliminated as the turbocharger reaches operating RPM and the supercharger is effectively disconnected by the bypass valve. Parallel arrangements typically require the use of a bypass or diverter valve to allow one or both compressors to feed the engine. If no valve were employed and both compressors were merely routed directly to the intake manifold, the supercharger would blow backwards through the turbocharger compressor rather than pressurize the intake manifold, as that would be the path of least resistance. Thus a diverter valve must be employed to vent turbocharger air until it has reached the pressure in the intake manifold. Complex or expensive electronic controls are usually necessary to ensure smooth power delivery. Disadvantages. The main disadvantage of Twincharging is the complexity and expensive components. Usually, to provide acceptable response, smoothness of power delivery, and adequate power gain over a single compressor system, expensive electronic and/or mechanical controls must be used. In a spark ignition engine, a low compression ratio must also be used if the supercharger produces high boost levels, negating some of the efficiency benefit of low displacement. Commercial availability. The concept of Twincharging was first used by Lancia in 1985 on the Lancia Delta S4 Group B rally car and its street legal counterpart, the Delta S4 Stradale. The idea was also successfully adapted to production road cars by Nissan, in their March Super Turbo. Additionally, multiple companies have produced aftermarket Twincharger kits for cars like the Subaru Impreza WRX, Mini Cooper S, Ford Mustang, Toyota MR2. The Volkswagen 1.4 TSI is a 1400cc engine utilized by numerous automobiles of the VW Group that sees use of both a turbocharger and a supercharger, and is available with 8 power ratings, 103 kilowatts at 5,600 RPMs. 220 Nm at 1,500 4,000 RPMs VW Golf E, VW Jetta 5, and VW Charan. 110 kilowatts at 5,800 RPMs. 220 Nm at 1,250 4,500 RPMs Seat Ibiza 4. 110 kilowatts at 5,800 RPMs. 240 Nm at 1,500 4,000 RPMs VW Passat 6, VW Passat 7, VW Charan, 110 kilowatts at 5,800 RPMs. 240 Nm at 1,750 4,000 RPMs VW Charan 2, VW Tiggan, Seat Alhambra, 118 kilowatts at 5,800 RPMs. 240 Nm at 1,500 4,500 RPMs VW EOS, VW Golf 6, VW Jetta 6, 125 kilowatts at 6,000 RPMs. 240 Nm at 1,500 4,500 RPMs VW Golf E, VW Jetta 5, VW Charan, 132 kilowatts at 6,200 RPMs. 250 Nm at 2,000 4,500 RPMs VW Polo 5, Seat Ibiza Cupra, Angstrom Coda Fabia 2, 136 kilowatts at 6,200 RPMs. 250 Nm at 2,000 4,500 RPMs Audi A1. The second-generation Volvo XC90 T6 and T8 models use a twin-charged 1969cc engine. Alternative systems. Anti-lag system Twincharging's largest benefit over anti-lag systems in race cars is its reliability. Anti-lag systems work in one of two ways, by running very rich AFR and pumping air into the exhaust to ignite the extra fuel in the exhaust manifold, or by severely retarding ignition timing to cause the combustion event to continue well after the exhaust valve has opened. Both methods involve combustion in the exhaust manifold to keep the turbine spinning, and the heat from this will shorten the life of the turbine greatly. Variable geometry turbocharger A variable geometry turbocharger provides an improved response at widely varied engine speeds. With variable incidence under electronic control, it is possible to have the turbine reach a good operating speed quickly or at lower engine speed without severely diminishing its utility at higher engine speed. Sequential twin turbochargers Sequential turbocharger systems provide a way to decrease turbo lag without compromising ultimate boost output and engine power. Nitrous oxide Nitrous oxide is mixed with incoming air, providing more oxidizer to burn more fuel for supplemental power when a turbocharger is not spinning quickly. This also produces more exhaust gases so that the turbocharger quickly spools up, providing more oxygen for combustion, and the N2O flow is reduced accordingly. The expense of both the system itself and the consumable N2O can be significant. Water injection. For more engine power, and to augment the benefits of forced induction, an aftermarket water injection system can be added to the induction system of both gasoline and diesel internal combustion engines. References. External links: http www.glencarcongress.com 08/inside VWS new HTML